Hi everyone, and welcome to the second video in this calculus series. Today we'll be talking about the derivative. The derivative is a core concept in calculus and is used to determine the rate at which a function is changing. This proves very useful when solving for the rate at which solutions will mix or finding the total number of sales of a given item over a given time period. The applications are countless in all sorts of fields. In the last video, we got an introduction to the derivative by finding the limit of our secant line as one point approached our point in question. If you want to check out that video, then the link will be in the description, and it will take you to our intro to calculus and limits video. Alright, let's jump into this. Alright, so we left off talking about derivatives at this point here. Now we realized that to solve this limit, we had to factor out a difference of squares. So we get the limit as x approaches 2 for x plus 2 times x minus 2 over x minus 2. And we see that we have a like term on top and bottom. We can cancel them out. If you look back to the last video, you'll see an explanation as to why this is allowed. But for here, we're going to carry on. This leaves us with the limit as x approaches 2 of x plus 2. And now we can just plug in and we get the answer to be 4. We know this is also equal to the slope of the tangent line at x equals 2. So the question is, can we streamline this process to come up with the representation for the rate of change at any point on this curve? The answer is yes, but we need to change a little bit of notation. So I've redrawn our function here with some newly labeled points. We have an arbitrary point x, and we also have another point h, and the distance between them we'll call delta h, or change in h. Now we're going to solve the same limit as before, just using more general terms. Keep in mind, this is still going to be the same as the slope equation. We're just rewriting it in a more general sense. Let's see what happens when we try to solve it. So we're going to take the limit, wrong color. Let's do this in white. Let's take the limit as delta h approaches 0 of, let's represent our function's output in a more general sense. So we know our function is f at x equals x squared. So we're going to do x plus our point h all squared minus x squared, which is the other point on our line, all over, we'll have delta h. Now, if we try to evaluate this and just plug in 0 for delta h, we're going to get a case that we can't really solve. It's going to give us x plus 0 squared minus x squared over 0, which also equals 0 over 0. This gives us an indeterminate form, and like last time, we're going to need to manipulate this limit before we can actually solve it. So I'm going to rewrite our limit. We have the limit as delta x approaches 0 of x plus h squared minus x squared all over change in h. And I'm going to go ahead and try to expand these brackets. So we have limit as delta x approaches 0 of x squared plus 2xh plus h squared minus x squared all over delta h. Now, if we look in our numerator, we see our x squared terms cancel out. So we're left with our limit as delta x approaches 0 of 2xh plus h squared all over delta x. And if we divide each term by x, then we see that what's left is our limit as delta h approaches 0 of 2x plus h. All we need to do now is plug in 0 for h, which gives us our answer as 2x. So now what we've done is we've found a function which represents the derivative of our function at any point that we would want to calculate it at. So let's say we wanted to find the rate of change at x equals -2. All you need to do is plug in -2 to x for our function, and we'd get the rate of change. For notation purposes, this is how we'd show that we're evaluating a limit or a derivative, sorry, at any given point. So we'd write f prime at x is equal to 2x, and then if we wanted to evaluate this at a given point, let's say x equals 3 or whatever, we could do f prime at 3 is equal to 2 times 3, which is equal to 6. So at x equals 3, our derivative would actually be equal to 6. Now that we know how to calculate the derivative for x squared, we can apply the same principles to find the derivative of any function. This is the definition of the derivative, and it is one of the first principles of calculus. The limit is as follows. The limit as delta x approaches 0 of f at x plus h minus f at x all over delta h. This is the first principle's definition of the derivative and can be used to find the derivative of any real function. Alright, so now that we know how to find derivatives using the first principle's definition, let's do some examples. First off, we have f at x equals x cubed. So to start off, let's apply the definition of the derivative. So we have f prime at x is equal to the limit as delta x approaches 0 of x plus h all to the power of 3 minus x cubed over delta h. Now we know if we try to plug in 0 right away, we're going to get a 0 over 0 situation, so that's not good. So what we're going to do is we're going to try expanding this. So we have the limit as delta x, or delta h, sorry, approaches 0 of x plus h cubed minus x cubed over delta h, which is equal to the limit as delta x approaches 0, and we're going to expand this. So the expansion is x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed all over delta h. Now if we first cancel out like terms, we see that our x cubed terms cancel out. So we have the limit as delta h approaches 0 of 3x squared h plus 3x h squared plus h cubed all over change in h. Now if we divide each term by h, we see that we have the limit as delta h approaches 0 of 3x squared plus 3x plus h squared. Oh boy, forgot this h. And to evaluate this limit, all we need to do is plug in 0 for h, which gives us 3x squared. So that's the answer. That is the derivative for the function f at x equals x cubed. Now we're going to do example 2. So I'm just going to copy and paste this. We're going to start this example down here. This one's a little bit more tricky. So we're going to do the same setup. We're going to say f prime at x is equal to the limit as delta h approaches 0. And we have square root x plus h minus square root x all over delta h. Here we know we have the same thing. If we plug in h as 0 right away, we're going to get a 0 over 0. So I'm not going to do that, and we're going to go ahead with solving. So looking at this, there's not much we can do. So the first thing that comes to my mind is to try to multiply by the conjugate. So if we do that, we're going to get the limit as delta h approaches 0 of square root x plus h minus square root x over delta h, all multiplied by square root x plus h plus square root x over square root x plus h plus square root x. Multiplying this by the conjugate allows us to simplify our numerator, and hopefully things will start to cancel out. So expanding this multiplication, we get the limit as delta h approaches 0 of x plus h minus x over delta h multiplied by square root x plus h plus square root x. Now if we cancel out like terms in the numerator, we get the limit as delta h approaches 0 of h over delta h multiplied by square root x plus h plus square root x. And we see if we divide by h that we get our limit to now be equal to the limit as delta h approaches 0 of 1 over square root x plus h plus square root x. Now all we need to do is plug in 0 for h, and we'll get our answer. Doing that, we get 1 over square root x plus 0 plus square root x. This simplifies to 1 over 2 root x. Alright, so there we have it. That was an introduction to derivatives. Thank you for watching. Drop a like and leave a comment, and we'll see you in the next video of our series. Thanks.